Welcome to this walkthrough of LeetCode problem number 1837, sum of digits in base k. In this problem, we'll explore how to convert numbers between different bases and calculate the sum of their digits. Let's dive in and break it down step by step. In this problem, we are given two inputs, a number n in base 10, which is the standard number system we use, and another number k, representing the base to which we want to convert n. After converting n to base k, we are tasked with calculating the sum of its digits in this new base. For example, if n is 34 and k is 6, we convert 34 from base 10 to base 6, and then add up the digits of this base 6 representation to get the result. The output should be the total sum of these digits. Let's first understand the input and output format. The input includes two integers, n, which is a positive number in base 10, and k, which is also a positive number and represents the base. The output is a single integer, the sum of the digits of n after the conversion. We'll now look at some examples to make the problem clearer. To understand the problem better, let's start with the first example. Here, n is 34 and k is 6. The goal is to convert 34 from base 10 to base 6. When we do the conversion, 34 becomes 54 foot in base 6. Once we have this base 6 representation, we compute the sum of its digits. In this case, the digits of 54 foot are 5 and 4, and their sum is 5 plus 4, which equals 9. So the output is 9. In the second example, n is 10 and k is also 10. Since the base we are converting to is the same as the original base, no conversion is needed. The number 10 in base 10 remains 10. Adding the digits of 10, which are 1 and 0, gives us a sum of 1. So the output in this case is 1. This demonstrates how the problem works when no actual base conversion is required. Now let's analyze a slightly more complex example. Here, n is 42 and k is 2. The goal is to convert 42 from base 10 to base 2, which is binary. The base 2 representation of 42 is 101,010. To find the solution, we add up the digits of 101,010. The digits are 1, 0, 1, 0, 1, and 0, and their sum is 1 plus 0 plus 1 plus 0 plus 1 plus 0, which equals 6. So the output for this example is 6. Additionally, it's important to note some constraints for this problem. The value of n can range from 1 to 1 million, and the value of k, the base, can range from 2 to 1 billion. These constraints help us understand the size of the input and the range of possible solutions. Edge cases, such as very small or very large values of n or k, should also be considered to ensure the solution works for all scenarios. Considering edge cases is crucial for solving this problem. Let's start with the smallest values for n and k. If n is 1 and k is 2, the conversion of 1 to base 2 still results in 1. Since there's only one digit, the sum of the digits is also 1. Now, for larger values of n and smaller values of k, such as n equal to 1 million and k equal to 2, the base 2 conversion results in a binary number with many digits. The sum of the digits in this case becomes the total count of ones in the binary representation of 1 million. For large values of k, when k is greater than n, the base conversion results in n being represented as a single digit in the new base. In this case, the sum of the digits is simply n. Another interesting edge case involves powers of k. For instance, if n is 64 and k is 8, converting 64 to base 8 gives 10. The sum of the digits in 10 is 1, since 1 plus 0 equals 1. Understanding such cases helps ensure that our approach is thorough and handles all possible scenarios. To solve the problem programmatically, we can use a simple algorithm based on the mechanics of base conversion. The key idea is to repeatedly divide n by k and collect the remainders. These remainders correspond to the digits of n in base k. As we calculate each remainder, we add it to a running total called sum_digits. The process continues until n becomes 0. Here's the step-by-step approach. First, initialize sum_digits to 0. Then, while n is greater than 0, compute the remainder of n when divided by k using the modulus operation. Add this remainder to sum_digits. After that, update n by performing integer division of n by k, which reduces n for the next iteration. Once n becomes 0, the sum of the digits is stored in sum_digits, and this is our final result. This algorithm is efficient and works well within the constraints of the problem. To solve this problem, we need to convert a number n from base 10 to base k and then calculate the sum of its digits in base k. One intuitive way to approach this is through a brute force method, where we simulate the base conversion process step by step. Here's how it works: we repeatedly divide n by k, extracting the remainder at each step, which represents a digit in base k. These remainders are then added together to get the desired sum. The process continues until n becomes 0. This approach is simple to implement and works efficiently for this problem because the number of divisions we perform is proportional to the number of digits in the base k representation. To break it down, you start by initializing a variable, say total_sum, to 0. Next, as long as n is greater than 0, you compute the remainder using n%k, which gives you the least significant digit in base k. You add this remainder to total_sum and then update n by performing integer division with k to remove that digit. Once the loop ends, you return the total sum. This straightforward method directly addresses the problem requirements without any unnecessary complexity. When we analyze the brute force approach, we find that it is already optimal for this problem. The number of iterations in the loop corresponds to the number of digits in the base k representation of n, which is proportional to the logarithm of n with base k, or log_k, n. As a result, the time complexity of this approach is O log_k, n. Additionally, since we don't use any extra data structures and perform the calculations in place, the space complexity is O, 1. There are some key insights that make this approach efficient. First, the core of the problem revolves around simulating how numbers are represented in base k. Using modulus and division operations is a direct and efficient way to extract these digits. Second, the sum of digits in base k is simply the sum of the remainders obtained during this process, meaning we don't need to explicitly store or construct the base k representation. This makes the algorithm not only computationally efficient but also memory efficient. Given these observations, the brute force method is the ideal strategy. It balances simplicity and efficiency, avoiding unnecessary overhead introduced by alternative methods like constructing strings or lists to represent the digits. When comparing approaches, the brute force method stands out as the best choice for this problem. Its main advantages are its simplicity, memory efficiency, and reliance on straightforward mathematical operations to directly solve the problem. It doesn't require any additional steps like storing digits, which keeps the space usage minimal. On the other hand, an alternative approach, such as constructing the base k representation as a string or list, might have some benefits in terms of debugging or visualizing the digits, but it introduces significant drawbacks. These include higher space complexity from storing the digits explicitly and additional computational overhead for string manipulation. For a problem like this, these trade-offs are unnecessary. The brute force approach not only meets the problem requirements efficiently but also avoids the downsides of additional complexity. While alternative methods could be useful if we needed the full base k representation for some other purpose, that is not the case here. This makes the brute force method the clear and optimal choice. The problem requires us to convert a number from base 10 to another base, denoted as base k, and then calculate the sum of the digits in this new base. To achieve this, we need a clear understanding of the base conversion process. Base conversion works by repeatedly dividing the number by the target base and recording the remainders at each step. These remainders represent the digits of the number in the new base, starting with the least significant digit, which is the rightmost one. We also need to set up some variables for the algorithm. Specifically, we have the input variables, the given number n and the target base k. The output variable will store the sum of the digits in base k, which we'll calculate step by step. To do this, we initialize a variable called total_sum to accumulate the sum, and another variable, current, to keep track of the number as we repeatedly divide it during the conversion process. Now, as we perform the base conversion iteratively, we keep dividing the current number by the base and extracting the remainder at each step. This remainder represents the next digit in the base k representation. We add this remainder to total_sum, which accumulates the digits sum as we go. After processing the remainder, we update the current value by performing integer division with k. This operation effectively removes the least significant digit in base K, preparing current for the next iteration. Once current becomes 0, the conversion process is complete, and total_sum holds the final result, which we return as the sum of the digits in base K. A few key observations can deepen our understanding of this algorithm. First, the remainders from the division process directly map to the digits in the new base, from least to most significant. Second, by summing these remainders on the fly, we avoid the need to store or reverse the digits, making the algorithm both efficient and straightforward. The efficiency of the algorithm is notable. It runs in log_k(n) time because the number of iterations corresponds to the number of digits in the base K representation. Additionally, the algorithm gracefully handles edge cases, such as when n is 0 or when k equals 10, and operates correctly even if k is larger than n. The algorithm is also extremely space efficient, as it relies solely on primitive variables like integers. This simplicity means we avoid using additional data structures, such as arrays or strings, to store intermediate results. The operations involved are straightforward but powerful. The modulo operation extracts the least significant digit in base K, integer division removes this digit, and addition accumulates the sum. To bring this process to life, let's look at an example. Suppose n is 34 and k is 6. We initialize current to 34 and total_sum to 0. In the first iteration, we compute 34 mod 6, which gives 4, representing the least significant digit in base 6. Adding this to total_sum updates it to 4. We then update current to 34 divided by 6, which is 5. In the second iteration, we calculate 5 mod 6, yielding 5 as the next digit in base 6. Adding this to total_sum results in 9. Finally, we update current to 5 divided by 6, which is 0, signaling the end of the loop. At this point, since current is 0, the algorithm terminates, and we return the total_sum, which in this example is 9. This example illustrates how the algorithm efficiently computes the sum of digits in base K without needing additional storage. We can also optimize the process further by leveraging the early termination condition. The loop exits as soon as current becomes 0, ensuring no unnecessary iterations. Additionally, the algorithm avoids explicitly storing the digits, further reducing memory usage. In terms of complexity, the time complexity is log_k(n), as the number of iterations is proportional to the number of digits in base K. The space complexity is O(1), since no extra space is required beyond the primitive variables. The final implementation of the algorithm is both concise and elegant, relying on a simple while loop to perform the computations. By directly summing the remainders during base conversion, it ensures that the solution is both time efficient and space efficient. This solution efficiently calculates the sum of digits of a number n when represented in base K. Here's the breakdown. 1. Initialize digit_sum. We start by initializing digit_sum to 0. This variable will accumulate the sum of digits in base K. 2. Base conversion and summation. Using a while loop, we repeatedly divide the number n by the base K. n%k gives the remainder, which corresponds to the rightmost digit in base K. This value is added to digit_sum. n // performs integer division, effectively removing the rightmost digit from the number when represented in base K. The loop continues until n becomes 0, indicating that all digits have been processed. 3. Return the result. Finally, the accumulated digit_sum is returned as the output. ## complexity analysis. Time complexity. The loop runs log_k(n) times, as each division reduces n by a factor of k. Space complexity. The algorithm uses O(1) extra space, since no additional data structures are used. This approach is optimal, handles edge cases, like small values of n and k, and adheres to the constraints of the problem. This is the Java implementation for LeetCode problem number 1837, sum of digits in base K. The logic mirrors the Python solution, where the number is repeatedly divided by the base K, and the remainders, digits in base K, are summed. Unlike Python, Java requires explicit type declarations and uses integer division / for truncation. The method is encapsulated in a public class named solution to adhere to LeetCode submission format. To solve this problem, we start with the decimal number 34 and aim to convert it into its base 6 representation. Once we have the digits of the base 6 number, we'll compute their sum. Initially, we set n to 34, k to 6, and digit underscore sum to 0. In the first iteration of the loop, we calculate n%k, which gives us 4, the last digit of 34 in base 6. This value is added to digit underscore sum, making it 4. We then update n with integer division by k, resulting in n equals 5. In the second iteration, we repeat the process, n%k gives us 5, the next digit in base 6, which is added to digit underscore sum, updating it to 9. Once again, we perform integer division on n, which now becomes 0. At this point, the loop ends because n has reached 0. After exiting the loop, we can conclude that the base 6 representation of 34 is 54, and the sum of its digits is 9. Therefore, the output for this example is 9. Moving on to a new example, we now take n equals 10 and k equals 2. Here, the goal is to convert the decimal number 10 into its binary representation, which is base 2, and then sum the digits of that representation. Initially, we set n to 10, k to 2, and digit underscore sum to 0, preparing to execute the same iterative process. In the first iteration of the loop, we calculate n%k, which results in 0, the last digit of 10 in its binary form. Adding this value to digit underscore sum keeps the sum at 0. We then update n by performing integer division by 2, setting n to 5. In the second iteration, n%k results in 1, the next binary digit, which is added to digit underscore sum, updating the sum to 1. We again perform integer division, reducing n to 2. For the third iteration, n%k gives 0, which is added to the sum, leaving digit underscore sum unchanged at 1. After dividing n by 2, it becomes 1. Finally, in the fourth iteration, n%k results in 1, the next binary digit. Adding this value to digit underscore sum updates the sum to 2, and integer division reduces n to 0. With n now equal to 0, the loop terminates. We can now determine that the binary representation of 10 is 1010, and the sum of its digits is 2. Therefore, the output for this example is 2. For another example, let's consider n equals 7 and k equals 7. Here, we aim to convert the decimal number 7 into its base 7 representation and calculate the sum of its digits. As usual, we initialize n to 7, k to 7, and digit underscore sum to 0 before starting the loop. In the first iteration of the loop, we calculate n%k, which results in 0, the last digit of 7 in base 7. Adding this value to digit underscore sum keeps the sum at 0. We then update n using integer division by 7, which reduces it to 1. In the second iteration, n%k results in 1, the next digit of the base 7 representation. Adding this value to digit underscore sum updates the sum to 1, and integer division reduces n to 0. At this point, the loop ends because n has reached 0. The base 7 representation of 7 is 10, and the sum of its digits is 1. Therefore, the output for this example is 1. This process illustrates some key observations. At each iteration, we extract the last digit of the number in base k using the operation n%k and add it to our running total, digit underscore sum. To remove the last digit, we reduce n by performing integer division, and // equals k. The loop continues until n becomes 0, at which point all digits have been processed. This approach is efficient because it processes one digit at a time, making it suitable for any positive integer n and any base k greater than 1. To analyze the time complexity of this algorithm, let's start by understanding its key operations. Within each iteration of the while loop, the algorithm performs two main mathematical operations, calculating the remainder of n divided by k using n%k, and performing integer division with n // equals k to reduce the value of n. These are both constant time operations. Now, the number of iterations the loop executes depends on how many times n can be divided by k before reaching 0. This is directly related to the number of digits n has when represented in base k. Mathematically, the number of digits in base k can be approximated as log_k, n. Using the change of base formula, this becomes log n/log k. Since each iteration involves constant time operations, the time complexity per iteration is O(1), and we will use this to determine the overall time complexity in the next steps. Now, we can compute the total time complexity by combining the number of iterations and the per iteration cost. Since the loop runs approximately O log n/log k iterations, and each iteration has a constant cost of O(1), the overall time complexity of the algorithm is O log n/log k. Moving on to space complexity, let's examine the memory requirements. The algorithm uses two scalar variables, digit_sum, which keeps track of the cumulative sum of digits, and n, which is updated iteratively during the base conversion. Both of these are simple integers, requiring constant space. Additionally, the algorithm does not rely on any data structures such as arrays, lists, or recursion stacks, so it does not consume extra memory. As a result, the overall space complexity of the algorithm is O(1), making it extremely space efficient. Let's compare this optimized approach to a potential brute force method. A naive solution might involve generating all the digits of n in base k and storing them in a data structure like a list, followed by summing the digits. While this approach works, it introduces additional space complexity of O log n/log k, since the digits need to be stored explicitly. In contrast, the current algorithm avoids this by directly calculating the sum of digits without creating additional storage. This optimization reduces the space complexity to O(1), while maintaining the same time complexity of O log n/log k. To summarize, the optimized algorithm achieves both time and space efficiency, with a time complexity of O log n/log k and a minimal space complexity of O(1). This makes it a significant improvement over brute force approaches, especially for large inputs, as it minimizes memory usage while efficiently computing the result. One of the most common mistakes in this problem is misunderstanding how to convert a number into base k. Some may try to directly compute the base k representation without using the division and modulus approach. Remember, base conversion requires repeatedly dividing the number by k and collecting remainders, which represent the digits in reverse order. Skipping this process often leads to incorrect digit sequences. Another frequent issue is assuming that leading zeros are part of the base conversion. While leading zeros don't affect the sum of digits, they can cause problems if your logic relies on the number of digits. Additionally, some confuse base conversion with string formatting, treating it as a manipulation task rather than a mathematical process. This confusion can result in errors, especially when dealing with large numbers or less common bases. Another area where mistakes occur is overlooking edge cases. For instance, when n equals 0, the sum of digits should also be 0. Similarly, for very small values of k, such as k equals 2, failing to handle edge cases can lead to division errors or even infinite loops. Efficiency is another critical concern. Using brute force methods for large inputs can severely impact performance. Instead, base conversion can be optimized using logarithmic calculations, making it more efficient for large numbers. Ignoring these optimizations may lead to timeouts, especially in coding competitions or interviews where input sizes can grow significantly. Interviewers often want to test your understanding of the base conversion process, so it's important to clearly explain the division remainder method. This is a common point of confusion for many candidates. It's also helpful to recognize patterns, such as how the sum of digits in any base is always less than or equal to the original number. Time complexity is another key discussion point. While a brute force method may suffice for small inputs, larger inputs require more efficient solutions, such as using logarithmic shortcuts. You should also be prepared for variations of the problem. For example, an interviewer might ask you to compute the product of digits instead of their sum or impose additional constraints to test your adaptability. There are several related problems that can help solidify your understanding of base conversions and digit sums. For example, LeetCode 168 involves converting numbers to a base 26 alphabetic system, similar to Excel column titles. LeetCode 405 focuses on converting numbers to hexadecimal, which uses base 16. In contrast, LeetCode 171 reverses the process, interpreting a base 26 representation as a number. LeetCode 258 explores digit sums and their properties, offering a conceptual link to this problem. When considering alternative approaches, an iterative base conversion using a while loop is straightforward but may be slower for large numbers. On the other hand, mathematical optimizations, such as leveraging logarithmic properties, can make the process more efficient but require a deeper understanding of the math involved. Another approach to base conversion involves using string manipulation and built-in functions. For example, Python's format or Java's integer dot-to-string can handle the conversion efficiently. These methods are particularly useful when performance is critical, as they are optimized internally. However, in interview settings, you may be required to manually implement the conversion process to demonstrate your understanding of the underlying mechanics. While these built-in functions provide a shortcut, relying on them without grasping the mathematical principles might limit your ability to adapt to variations of the problem or to handle edge cases effectively. Great job! We've successfully tackled problem number 1837 and learned how to convert numbers between bases. Remember, mastering these foundational skills is crucial for solving more complex problems. Stay curious, keep practicing, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!